Hi there. In this video, we'll be going through some practice problems related to gas laws. In your chemistry class, you may have looked at things like Boyle's law or Charles' law, and I thought it would be good for us to do some practice problems related to those. You can check out the link below to go to a small worksheet that has a few problems, and we'll go through each of those problems. What you may want to do is pause the video, try to work things out on your own, and then ones that you get hung up on, you can come back and watch the video related to that problem. Okay. So I'm going to be reading the questions off of my phone, and I'll display that on the board here, and then we'll go through the solution and do the calculation and things like that. Okay. So a couple things to keep in mind, right? Remember that the gas laws, no matter which one you're talking about, Boyle's or Charles or Avogadro, they basically can all be found within the ideal gas law, right? This idea that PV, pressure times volume, is equal to moles times a constant times temperature, okay? And so that gas constant is here, this 0.08206, okay, that's the number, but then look at the units. It's a volume unit in liters times atmospheres, a pressure unit, divided by moles and divided by Kelvin, okay? So you notice that in general terms, generally speaking, when we want to use the ideal gas law, we need to make sure that pressure is in the units of atmospheres, volume is in the units of liters, and temperature is in the units of Kelvin. In the gas laws that we're going to look at today, these derived gas laws, okay, usually what you can do is just make sure that you have the same units on both sides of the equation. There's lots of pressure units like bar and torr and pounds per square inch and pascals, okay, or atmospheres, okay. All of these units are ways to describe pressure. And basically for the problems that we'll look at today, any starting unit is okay, provided that it's the same unit on both sides. Same is true for volume. If we're using the ideal gas law, we want to make sure that volume is in liters, but there's lots of ways to describe volume. And as long as that unit is the same on both sides of the equations that we'll set up, it's okay. The one exception here is temperature. One of the places that I see that students get hung up on the gas laws all the time is not changing temperature units, okay, from something other than Kelvin into Kelvin, okay? The gas laws only work if you've got temperature in the units of Kelvin, right? All right, so let's take a look at our first problem. So what we're asked is, well, what will be the new volume of the gas, assuming that moles and temperature remain constant, if the pressure of 1.21 liters of neon is increased from 0.75 torr to 1.73 torr, okay? So let's kind of keep track of our units here. So we've got some sample of neon gas, okay? One thing that we're told is that we've got two pressures. We have an initial pressure, a P1, of 0.75 torr. And we're told that that pressure is increased up to 1.73 torr. Okay. So one of the things that we see here is that this sample of gas is undergoing a change in pressure. And so what the problem is asking us is, if the pressure changes, what happens to volume, right? We're told that the volume initially, okay, is equal to 1.21 liters, and we're asked, what's the new volume? Okay, what's the new volume, okay, if our sample of neon undergoes this pressure change? Notice one of the things that the problem tells us. It tells us that moles and temperature remain constant, okay? Throughout the worksheet, I've tried to explicitly say which of these four variables we're leaving constant. But lots of times that's not really included in the problem. Okay? These kinds of gas law problems that we're going to be talking about are always done the same way. They always talk about only two of these four variables. Okay? They tell you the initial conditions of both variables. They tell you that a change happens, okay? And they tell you what that change is for one of the variables. And they ask you to calculate the change for the other variable, right? In this problem, we're told that pressure changes. And so our question is, well, we knew what the volume was initially, but once this pressure change happens, what happens to volume? Okay. The only way that these questions really work is if the other two variables here are held constant. And so I've explicitly told you that moles and temperature remain constant. So what is the gas law that we should use to solve this problem? Well, maybe you know that we need to use Boyle's law. Maybe you know that we want to say P1 V1 equals P2 V2. But how do we get there? How do we know that that's what we want to use? Okay? What we can do, the strategy that we can use, if you don't know a particular gas law or you were asked to memorize them and you can't quite remember what it was, as long as you can remember the ideal gas law, you're set. Okay? So PV equals nRT. What we're going to try to do with this has a total of four variables, right? Pressure, volume, moles, and temperature are all variables. They can all change, right? R can never change. It always must be the same number. It's a constant, right? So let's try to get the variables in our problem that are changing on one side of the equation and everything that's staying constant on the other side of the equation. Well, in this first problem that we're doing, that's really easy because that's already the way that it's set up. We're told that we've got a pressure and a volume. The pressure and the volume are changing, and we're told that moles and temperature are going to remain constant. Okay? So we've got pressure on one side, pressure and volume, the things that are changing on one side of the equation, all the things that are remaining constant on the other side of the equation. And so what we can say is that initial pressure and that initial volume are equal to this constant, but also the new pressure and the new volume, that product is also equal to this constant. Okay? So we can just kind of cancel out the constant that's in the middle and say that P1 V1 is equal to P2 V2. Okay? So this law, which is called Boyle's law, comes from this ideal gas law by putting the things that change on one side of the equation and everything that stays constant on the other side of the equation. So how do we solve for this? Well, we've got P1, we've got P2, we've got V1, and we're solving for V2, right? So let's just put those numbers in place. And remember what I said a little while ago, the units don't necessarily matter as long as they're the same units on both sides of the equation. So P1 is in torr, that's okay as long as P2 is also in torr. V1 is in liters, that's fine, and it means that V2 will also be in liters, right? So we can say in our problem, we can say that 0.75 torr times 1.21 liters is equal to 1.73 torr times V2, right? V2 is what we're solving for, so we want to isolate that variable. We can do that by dividing both sides of this equation by 1.73 torr. Okay? This whole thing will cancel this with this, and all that's left here is V2. Then on this side of the equation, none of the numbers are going to cancel out per se, but we see that the units of torr and torr cancel in the numerator and denominator. The only unit that's left is liters, so that's good. And so now all we need to do is just do the math here. So let me bring up my calculator and we'll give that a shot. All right, so we'll say 0.75 times 1.21 divided by 1.73. Okay, and so we see that that equals 0.524, and so I think by significant digits, I'm just going to say that V2 is equal to 0.52 liters. Okay. So look what happened here. Okay, let's see if this makes some physical sense. Okay, so it's P1 V1 equals P2 V2. So if all this stuff is a constant, if nRT is going to be a constant, if pressure goes up, then volume is going to have to go down, right? So that when we multiply them together, we end up with that same constant. Okay? And look what's happening in the equation. P1 to P2, we're more than doubling the pressure, right? We're going from 0.75 to 1.73. Okay? We're more than doubling it, so we should be cutting the volume by more than half, right? And that's exactly what we're doing. We're going from 1.21 liters down to just above a half a liter. Okay, so more than doubling the pressure cuts the volume in half, right, or more than half. Okay, let me erase this from the board and we'll try another one. All right, let's take a look at our next problem here. We're told that we've got a sample of argon gas. We're told that it initially has a temperature of 54 degrees Celsius. And it's asking what's the new temperature, right? So we don't know T2. Well, we can calculate that as long as we're told what's happening to one other of these 4 units. Well, that's what we're told. We're told that the pressure of this sample of argon is increasing from 1.1 atmospheres up to 1.8 atmospheres. Okay. So in this particular problem, we're asked if we change the pressure, what happens to temperature? Okay. And notice again what I explicitly told you in the problem, that's not always there. T and P are changing, but what we're saying is that N and V will stay constant. Okay? All right, so maybe you already know the relationship between pressure and temperature, but let's do what we did before. Let's use this idea of the ideal gas law to calculate what equation we should use. Right? Remember what our strategy is. We want to get the things that are changing on one side of the equation and everything else on the other side of the equation. Okay? So initially we've got PV equals nRT. Let's divide both sides by T and divide both sides by V. And what does that do? The V's cancel, and so now I've got P and T on one side of the equation. The T's cancel over here, and so now on this side of the equation, I've got N, R, and V. All the things that we know in this problem are staying constant, right? We're told that N and V are staying constant, and we know that R is always constant, right? So we have P over T is equal to NR over V. If we say that P1 over T1 is equal to NRV, NR over V is also equal to P2 over T2. We can cancel out the stuff that's in the middle and say that P1 over T1 is equal to P2 over T2. Okay? So this is the relationship that we want to use for this particular problem. We're going to find out what happens to temperature when we change pressure. Right? Now remember, one of the things that I said earlier is that these kinds of problems, the units for pressure and volume don't necessarily matter as long as they're the same on both sides of the equation. But for temperature, it's critical that we put temperature in units of Kelvin. Okay? Let's remember what the relationship is between Kelvin and Celsius. So that the temperature in Kelvin is equal to the temperature in Celsius plus 273 Okay. So before we go any further, let's write T1 in Kelvin. Okay, so let me bring up our calculator again. And we can say we're starting with a temperature of 54 degrees Celsius. Let's add to that 273.15, and that equals 327.15 Kelvin. Okay. We know P1 and we know P2. We now know T1 in Kelvin. Let's solve for T2. Okay. Using our equation here. So we can say 1.1 atmospheres divided by 327.15 Kelvin is equal to 1.8 atmospheres divided by T2. Okay. So we need to isolate the variable T2. That's what we're trying to solve for. So how can I do that? Well, the clever thing to remember here is to cross multiply and divide. We'll multiply both sides of the equation by this denominator and by this denominator, okay? And then divide by this numerator. All right, so let's do that. Let's cross multiply first. So we can multiply both sides by T2, and so what we end up with is T2 times 1.1 atmospheres is equal to 1.8 atmospheres times 327.15 Kelvin. Okay. Right? We took this denominator, moved it up here. We took this denominator, moved it up here. Okay. Now we want to do the dividing part, right? So now let's divide both sides by 1.1 atmospheres. Okay. 1.1 atmospheres is going to cancel top and bottom and just leave me with T2 on this side of the equation. Here I've got 1.8 atmospheres times this temperature divided by 1.1 atmospheres. Well, none of the numbers cancel, but atmospheres cancels in the numerator and denominator. And so now the only unit left is Kelvin. Okay? So let's do that math. We'll say 1.8 times 327.15 divided by 1.1. And we end up with 535.34 Kelvin. Okay, so we've got T2 in Kelvin. I'll go ahead and write that. We've got T2 is equal to 535.34 Kelvin. But if you think back to our problem, we wanted the answer in degrees Celsius. So we're going to need to convert this Kelvin temperature back into degrees Celsius, right? To see which one of these are correct. So let me bring up the calculator again. Here's our temperature in Kelvin. Let's turn it back into degrees Celsius. How do we do that? We've got the Kelvin temperature. We want to solve for degrees Celsius. So that means we're going to subtract 273.15 from our temperature in Kelvin, right? We subtract this number from both sides and we isolate degrees Celsius on one side of the equation. So let's subtract 273.15 and what we get is 262, and by significant figures I think that's what I want, 262 degrees Celsius. Okay. All right, so we have our new problem on the board. We're asked to imagine a 1.4 liter balloon that contained a certain amount of helium. We're asked what would the new volume be if a certain amount of that helium leaked out of the balloon. Okay? So we're asked to come up with a relationship between moles and volume. So what's the relationship? I'll write that here. What's the relationship between moles and volume, right? So we're given an initial volume. We're told that the initial volume of the balloon is 1.4 liters, and we're told to calculate the new volume, right? That's what we don't know. We're given an initial amount of helium gas. We're told that initially there is 0.060 moles of helium. And we're told that some of that helium leaks out. We're told that 0.018 moles of helium leaks out of the balloon. Okay? So what is N2 in this problem? N2 is the amount that's still left in the balloon. A little bit of a trick here, right? So N2 is equal to 0.060 minus the amount that leaks out, which we're told is 0.018. And so what is that going to be? That's going to be 0.042 moles. Okay, so N2 is equal to 0.042 moles of helium. Okay, so that's our gas here. So we need this relationship between moles and volume. Well, what is it? In the problem, hopefully you noticed that we explicitly said that we're going to leave pressure and temperature constant in this problem. Okay, so we can use our ideal gas law to figure out what that relationship is. Okay, maybe you already know it. Maybe you can just look it up. This is Avogadro's law, but we can figure it out from the ideal gas law. So let's give that a try, right? So we can start with PV equals nRT, and we can try to isolate on one side of the equation only the things that are changing, okay? So we can divide both sides of this equation by P and by N, okay? Look what happens if we do that. The P's cancel, right? On this side of the equation, the n's cancel on this side of the equation. So over here, all that we're left with, RT over P, only the things that are staying constant. Okay? On this side of the equation, we have the V and the N, only the things that are changing. Okay? So V over N equals RT over P, V1 over N1 equals RT over P equals V2 over N2, right? If these things change, both of these ratios have to equal RT over P. Of course, we can kind of cross that out and just say that V1 over N1 is equal to V2 over N2. Okay. You might see this written the other way, where it's N1 over V1 equals N2 over V2. Right? Either way, this relationship still holds, that it's the ratio of moles and volume, okay, that are equal to each other. All right, so let's see if we can calculate this out. We've got V1 and we've got both of the n's. Okay, what we're looking for is V2, right? So we can say that the 1.4 liters over N1, which is 0.06 moles, is equal to V2, that's what we're solving for, divided by 0.042 moles. Okay. So now we want to isolate V2. Well, we can do that pretty easily by multiplying both sides of the equation by 0.042. That's going to leave us with 0.042 moles times 1.4 liters divided by 0.06 moles, and that's going to equal V2, right? Moles and moles cancel. The only unit that's left is liters. So let's do that math. All right, so we can say 0.042 times 1.4 divided by 0.060. And that gives us 0.98, okay? All right, so V2 equals 0.98 liters, okay? And so does that make some physical sense? We told you at the beginning that there's a balloon that has a certain volume and it's got a certain amount of gas in it. If we let some of the gas leak out of it, what's going to happen to the volume of that balloon? It's going to get smaller, right? It's going to shrink because some of that gas has escaped, okay? All right, let me erase the board and we'll try the last problem on our worksheet. All right, so we see our last problem here on the board. We're asked, what was the initial temperature Okay, so what was the initial temperature? We're being asked what was T1 if a sample of gas that expanded from 0.89 liters to 1.1 liters has a current temperature of 92 degrees Celsius. Okay? So we're told what the current temperature is, the temperature after the change. We're told that that's now 92 degrees Celsius. Okay? If a sample of gas expands, right? And so V1 to V2, it expands from 0.89 liters up to 1.1 liters. Okay? So we're told to assume that pressure and moles are constant. So pressure and moles are going to stay constant. It's just volume and temperature that's changing. Okay? Well, we've been down this road before. How can we do this? You might know already that this problem uses what's called Charles' law, the relationship between volume and temperature. Okay? But again, let's figure that out using the ideal gas law, right? So if we start with this idea that PV equals nRT, let's get the things that are changing on one side of the equation, all the things that are staying constant on the other side of the equation. Well, V is over on this side, so let's try to get T on this side. We can do that by dividing both sides by T. And then we want to get P, since it's staying constant, let's get it onto this side of the equation. And we can do that by also dividing both sides of the equation by P. Okay? And look what happens. P in the numerator and denominator cancels out on this side of the equation. Okay? T on this side of the equation in the numerator and denominator cancel. And so what I'm left with is that V over T is equal to NR over P, right? The things that are changing on one side, all the things that are staying constant on the other side, right? So I can say V1 over T1 is equal to NRP, or NR over P, and so that has to also be equal to V2 over T2, right? So we can cancel this stuff out that's in the middle, and we can say that this relationship between V and T, what's called Charles' law, is V1 over T1 is equal to V2 over T2, right? And so that's what we'll use to solve this problem. Now, remember that anytime we're dealing with temperatures, we want those temperatures to be in Kelvin. Remember that the temperature in Kelvin is equal to the temperature in Celsius plus 273.15, right? And that means what we'll need later, right? The temperature in Celsius is equal to the temperature in Kelvin minus 273.15. Okay? So before we get started, we need to convert T2 into Kelvin. Well, we can do that pretty easily. Let's bring up the calculator. We know we've got 92 degrees Celsius, so Celsius plus 273.15 equals 365.15. So this temperature in Kelvin is 365.15 Kelvin. Okay. So let's use Charles' law to solve this equation. Well, we know, or solve this problem. We know V1 is 0.89 liters. Okay. We know T1 is what we're trying to solve for. T1 is our variable. And that's equal to V2, okay, which is 1.1 liter, over T2, which is our 365.15 Kelvin. Okay. So we need to isolate T1 on one side of the equation, get everything else on the other side of the equation, right? And so we can do some cross multiplying here and then dividing, right? So I can say that 0.89 liters times 365.15 Kelvin is equal to 1.1 liters times T1. Okay? and now I can divide both sides here by 1.1 liter, 1.1 liter, and that gets 1.1 on the top and bottom to cancel, leaving me only with T1 on this side of the equation, and I've got 0.89 liters times our temperature in Kelvin divided by another volume in liters. So liters in the numerator and denominator cancel, and so the only unit that I'm left with is Kelvin, which is a temperature unit. Okay? So I just need to do this math here. So let's run through that real quick. So I can say 0.89 times 365.15 divided by 1.1, and that equals 295.43, equals 295.43 Kelvin. Okay, well, 0.44 Kelvin. But remember, I'm going to want to put this into Celsius, right? So degrees Celsius is Kelvin minus 273.15. So I can just subtract 273.15, and I get 22.29, or say 22 degrees Celsius. Okay. So this video was exploring how to do some of the gas law problems. And like I said, you may have a list of those gas laws, like Boyle's law and Charles' law and Avogadro's law, that shows you the relationship between two of these four variables, as long as the other two remain constant. Okay? If you know them, or you have a list of them, you have a sense of how to use them based on the problems. If you can't remember the particular gas law that you need, you can always use this strategy that we put together, right? Where you take the ideal gas law, you put the things that are changing on one side of the equation and the things that are staying constant on the other side of the equation, right? I hope this was helpful. I hope you'll check back in for some other videos related to gas laws, like how to do some ideal gas law problems, how to do some stoichiometry using gases, and things like that. So again, I hope this was helpful. I'll see you next time.